You flip a switch, and boom, the light's on, just like that. It feels like magic, right? But it's not. It's actually the very end of this incredible, high-stakes journey that stretches for hundreds, sometimes even thousands of miles. So today, we're going to follow that journey, from the power plant all the way to your plug. I mean, it's something we totally take for granted. But behind that simple flick of a switch is this fascinating story of physics, power, and incredible precision. So let's pull back the curtain and demystify it, step by step. Okay, so our journey kicks off right where you'd think it would, at a power plant. This is where all that raw energy gets turned into electricity. But here's the thing. Right out of the gate, there's a huge problem. See, the way electricity is made isn't the way it needs to be to travel across the country. So it doesn't really matter if it's coming from splitting atoms, or burning coal, or harnessing the sun. All these power plants generate what we call alternating current, or AC. But the really surprising part, it's the voltage it starts at.
And yeah, that sounds like a ton of power, right? And hey, it is. But in the grand scheme of power transmission, this is actually considered, well, kind of low voltage. It's just not strong enough to push that electricity across the state, let alone the whole country, without losing most of its juice along the way. And here's why.
Okay, picture this. If you tried to send that 25,000-volt electricity straight down a wire for hundreds of miles, you'd lose a huge chunk of it as wasted heat. It's kind of like trying to force a massive amount of water through a super long, really skinny garden hose. Most of the energy just gets lost fighting the friction. Well, with electricity, it's the same idea. We just call that friction resistance.
So, how in the world do you solve this massive waste problem? I mean, you can't just make the wires infinitely thick. That's not practical. So you have to change the electricity itself. And that brings us to the unsung hero of our modern world, the step-up transformer.
And this really gets to the heart of the whole thing. There's a critical trade-off. You could send power with low voltage and high current, but like we just saw, that generates a ton of heat and waste. Or you can use high voltage and low current. By cranking the voltage way up, you can drop the current way down. And that is the secret sauce to making the whole grid efficient.
And this little formula right here shows us exactly why that works. Now, don't worry, we're not going to do a full-on physics lecture, but just look at the I for current. See how it's squared? That's the key. It means if you cut the current in half, you don't just cut the energy loss in half. No, you reduce it by a factor of 4. So bringing that current down has this huge exponential payoff in cutting down waste. And this is the amazing device that makes it all happen. A transformer is, believe it or not, remarkably simple. Just think of it as two coils of wire, right next to each other, but they don't touch. The current coming in on the first coil creates a magnetic field. That magnetic field then creates a totally new current in the second coil. And here's the magic trick. If that second coil has way more loops of wire than the first one, the voltage gets a massive boost.
All right, so now that we've transformed our electricity into this super efficient form, it's finally ready to hit the road on the electrical grid's superhighway.
And I am not kidding when I say superhighway. We're talking about boosting the voltage from that initial 25,000 volts all the way up to a mind-boggling 765,000 volts. It's that enormous electrical pressure that lets the power just fly across states, over mountains, and across rivers with hardly any energy loss.
You've seen them, right? Those giant steel towers marching across the landscape? Well, they are the literal backbone of the entire grid. And the wires they're holding up, they're not just simple copper wires. Oh no. They're usually thick aluminum cables wrapped around a steel core to make them super strong, designed to carry all that immense power and handle whatever Mother Nature throws at them.
Okay, so we've solved the efficiency problem. That's great, but we've just created a brand new one. I mean, 765,000 volts is so powerful, it can literally jump through the air. It's incredibly dangerous. You could never, ever plug your phone charger into that. So how do we tame this beast?
Well, funny enough, the exact same principle that let us crank the voltage up for the journey now lets us bring it back down for a safe delivery. And this doesn't happen all at once. It happens in a series of stages as the power gets closer and closer to your neighborhood.
Think of it like a voltage ladder, where each step down brings the power to a more manageable level. First, you've got a big transmission substation near a city, and that'll knock it down from 765,000 to maybe around 69,000 volts. Then, a smaller local substation takes it down even further to about 7,200 volts to be sent along your streets. And finally, you know that green box in your yard or that gray can on the utility pole? That little guy does the final, most important step, dropping it to the safe 120 or 240 volts that your home actually uses.
And the tech behind it is exactly the same, it's just running in reverse. This time, the electricity goes into a coil that has a lot of turns, and that induces a current in a second coil with far, far fewer turns. That simple switcheroo is what scales the voltage way, way down to a level that's safe and useful for everything in your house. And with that one last transformation, this epic journey that started hundreds of miles away at a gigantic power plant is finally over. The electricity has arrived. It's here, ready and waiting, right behind your wall socket.
So, let's just recap that incredible trip real quick. It starts at a pretty low voltage at the power plant. Then it gets stepped way up for an efficient trip across the country. After that, it's carefully stepped back down in a few different stages until it's finally safe enough to power your life. So, if there's one thing to take away from all this, it's that the ability to easily change voltage up and down, that's the real secret ingredient. That's what makes our entire electrical grid possible. It's the genius solution that solves two huge problems at once: how to send power over long distances without wasting it, and how to make it safe enough to use when it gets to us. It really is the unsung hero of our modern world.
You know, this whole system is an absolute marvel of engineering, but a lot of it is based on technology that's over 100 years old. So as we start moving towards things like renewable energy, smart grids, and all sorts of new demands on the system, it really makes you wonder, right? What is this incredible journey going to look like in the next 100 years?